Yeah, hi everyone. This is Prateek, and today we are going to look at chapter fourth of chemistry, 10th syllabus, which is carbon and its compounds. Yeah, hi everyone. This is Prateek. So I would like to invite all of you to this uh, revision session on carbon and its compounds. Please feel free to post your doubts. You can always reach out through the WhatsApp chat, or you can always put your messages on the chat window here. Let's wait for a few minutes till people join in, and we'll just begin in another minute or two. Right, so let's begin. Everyone who is joining in, just please feel free to put in your name in the chat window just below the channel on the video, so I can see Ruchir is here, and a few more are just joining in. I again welcome you all, and let's look at this chapter today. How to answer the questions that are there. Also, we'll try and see what are the major important points that are necessary to be known before the exams, which are upcoming in the next few days, in the coming month or so. So let's get into the topic and understand what this chapter really deals with. I'll also try and give you some tips on writing answers to some typical questions that are asked on carbonate compounds. At the same time, what are the points that you should remember, and how should you present that in the exam? So that's our agenda today. Let's begin. Let's understand how we can deal with this chapter going forward. Yeah. So the first things first is, how is carbon really occurring in nature? What is the occurrence of carbon? How do we find carbon in our surroundings? The most important is the carbon in found in atmosphere. It's also found in the Earth's crust. It's found in all living organisms. In fact, carbon is present in fuels. So, for example, in the atmosphere, it is present as CO2, as carbon monoxide. In the Earth's crust, it is present as coal. In all living organisms, there are multiple hydrocarbons as well as organic compounds that are found. It's present in wood, either in terms of cellulose, glucose. I can see a few more people joining in. There's Kritika and Anirudh. Good to see you. Uh, Anyone who joins in, please feel free to put in your name in the chat window, so I'm aware that you are there and I can connect and interact with you. Please feel free to ask questions during the session, so that we can connect and I can answer any of the queries that you have. Uh, Now, carbon, as I was saying, that carbon is present in the fuels as well. It's present in coal, it's present in charcoal, or coke, petroleum, and all the natural gases. So, yeah, Mehul also is here. That's nice. And then we have carbon present in compounds, which are carbonates, for example, calcium carbonate, or limestone, as we call it commonly. contains carbon. We also have hydrogen carbonates, for example, baking soda, which is sodium bicarbonate, also has an hydrogen carbonate in it. The All the aerated drinks that we drink has carbonic acid, which is nothing but hydrogen carbonates. And of course, carbon is found in free state, as it is found in diamond, or in graphite, or in fullerenes. You can see I've been able to put up some images for you. So the diamond image is pretty clear, the fuel image, as well as biogas image where my cursor is. So this is the biogas image, and you can also find petroleum extraction. This is an oil rig, on the seashore of the coast of a country. Wood, there is coal. These are again coal particles, bitumen particles. So all of these are basically rich sources of carbon in nature. Now, how is the bonding really that's there in general, and especially in carbon, that will look very shortly. So you'll see that we notice that carbon actually has. So I can see Mehul and Shreyas have also joined in. Okay, so we can see that carbon actually has 6 electrons, and all of these 6 electrons are arranged in an electronic configuration of 2 4, which means that the first shell contains 2 electrons and the second shell contains 4 electrons. Now, as it has 4 electrons, it can achieve stability, which is an octet, which means 8 electrons, only by either gaining 4 electrons or losing 4 electrons. But we'll see that carbon actually chooses to share 4 electrons with other atoms, neither gain nor lose. And that's because gaining and losing has a lot of energy that is required. 1 or 2 electrons is easy to gain or lose, but 4 electrons gaining or losing is a huge amount of energy exchange. And therefore, sharing 4 electrons with other atoms is what carbon mostly prefers. So yeah, so of course it does not gain 4 electrons, because it is difficult for 6 protons to hold 10 electrons. At the same time, it cannot lose 4 electrons, because it needs largest amount of energy to lose 4 electrons. So it ends up sharing 4 electrons, as we said, with other atoms to attain stability. This actually results in formation of covalent bonds. We'll shortly see how in detail can we understand covalent bonds. But this four sharing of electrons is what we call as being tetravalent. So tetravalent means having a valency of 4, and valency basically means the number of electrons. Please note the difference between valence electrons and valency. Valency means number of electrons that are lost or gained or shared, that are lost, gained, or shared. That is valency. Whereas shared, yeah. But whereas valence electrons means number of electrons in the outermost shell. In carbon situation, the valence electrons is 4, but valency also is 4. But if I give you another examples, for example, oxygen, the valence electrons is 6. Valence electrons is 6 in number, but valency is actually only 2, right? So that's typical of compounds. So you'll realize that oxygen, the valence electrons is 6 in number, but valency is only 2. So these are some of the important facets that you have to remember when you write answers. Please do not mix up. Students do end up mixing both the concepts pretty much. So that's one of the major reasons why carbon forms covalent bonds. Going further, let's understand what covalent bonds are. So basically, covalent bond is formed by sharing of electrons. Anytime that electrons are shared, we say that it is a covalent bond. Now, if one pair of electrons is shared, of course, you'll end up getting a single covalent bond. Whereas if multiple pair of electrons is shared, for example, two pair of electrons. Now, please note, two pair of electrons means each atom lends one electron, lends 2 electrons each. And therefore, for example, oxygen, when you form O2, it lends 2 electrons, and we'll shortly see how it really happens. So that forms a double covalent bond. And when we say 3 pairs of electrons are shared, each atom is giving 3 electrons, and that's how 3 pairs are formed, and that's a triple covalent bond. So formation of single covalent bonds is pretty typical in atoms like hydrogen. In fact, chlorine, bromine, fluorine, all of these atoms would show single covalent bonds. Now, let's understand how this bond typically would form. So, a common question that generally is asked is explain covalent bonds with a Louis diagram, and give an example of formation of covalent bonds, and explain the formation of covalent bonds. Sometimes it's directly asked as explain the formation of hydrogen or fluorine. So in that situation, most important is you have to write the atomic number. You have to write the electronic configuration. This is one of the most important points. Without writing electronic configuration, if we jump to the stage of just writing the number of bonds, you might lose a half mark or a mark there. So you write the atomic number, you write the electronic configuration or electronic arrangement, and then say that it has one valence electrons, and therefore it needs X number of electrons. In this case, it needs only one more to achieve stability. Please note here, duplicate is achieved and not octet. So that also has to be mentioned, that hydrogen needs to achieve a duplicate, and therefore it needs one more electron to be bonded with. So two hydrogen atoms share one pair of electrons, resulting in the formation of single covalent bond in hydrogen molecule. This is the way to write a Louis diagram, and we'll see some more examples of Louis diagram as we move forward. Similarly, if the question is how would you form a double covalent bond, for example, an oxygen, again the process remains the same. You mention the atomic number, that is okay. So there's someone else has joined in. I would be happy to know your name. Uh, the one with H2O and CO2. If you can just post in your name, I think I'd be more than happy to understand. Yeah. So the H2 and CO2 are all covalent bonds, by the way. Yes, that's right. H2O has both single covalent bonds, whereas CO2 has two double bonds. So we'll just look at how oxygen molecule is formed. So the atomic number of oxygen is 8, and therefore its electronic configuration is 2 6, and hence it has 6 valence electrons. It needs 2 more electrons to attain stability. So oxygen atoms share 2 pairs of electrons. Please note each atom is giving a pair of electrons, and therefore 2 pairs are formed. Now, once they are formed, you'll realize that they end up forming a double bond. Now, H2 and CO2 are covalent bonds. Just to answer the query, H2O actually forms 2 single bonds, and CO2 actually forms. So I'm drawing a structure for you. Another 2 bonds with oxygen. So you can realize that if I draw the crosses means the electrons by carbon, and the dots means the electrons by oxygen. Now you'll realize that carbon and oxygen form 4 covalent bonds, in fact, but the number of electron pairs that are formed are also 4. Cl2 also is a covalent bond. So all of these are covalent bonds. Now oxygens actually share 2 pairs electrons with each other to form a double covalent bond, and that's why the molecule is termed as O2. Now, if you look at triple covalent bonds, and please note triple is the highest amount of covalent bonds that you can form. So nitrogen, actually the atomic number is 7, and the electronic configuration is 2 5. So it has 5 valence electrons, and it needs only 3 more electrons to attain stability. We can very well mention here that there is an octet that is intended by nitrogen to be formed, and therefore 2 nitrogen atoms get together to share 3 pairs of electrons. So all these 3 electrons together will form a triple bond. These are the Lewis structures that can be drawn. There's so all of these Lewis structures can end up forming an N2 structure. And therefore we can write it as N triple bond N or N2. uh, a quick more question is, there should be, yes, definitely there should be 8 electrons that are shared, not atoms, 8 electrons shared, and they should have to achieve a complete octet. So NO2, in fact, not N2O, NO2 or MgO. In fact, it's always NO2 or MgO. So both of these, now MgO is more an ionic compound, but NO2 is more of a covalent compound that we can really look at. So these are a quick couple of quick looks at how double bonds and triple covalent bonds are formed. Now, here's another way to really look at these configurations. So you can see that these are actually the atomic structures of hydrogens which can share electrons, and we have 2 electrons shared by a pair of hydrogen atoms. Similarly, fluorine also shares two. These two electrons make one bond. Similarly, two electrons here make one bond in fluorine. In oxygen and carbon, as CO2, as I was mentioning, you'll find that carbon actually shares four electrons. So there are four pairs of electrons or four bonds that are formed. All the four bonds are covalent. In other manner, if you really see fluorine and carbon, you'll find that the yellow electrons of carbon are shared each with one blue electron of fluorine, and therefore there is a tetrafluoride molecule that is formed. So CF4 molecule is formed, which actually contains four covalent bonds again. So one quick point that we have to really note here is, again, a common confusion: two electrons means one bond. So that's a typical fashion. And also, covalent bonds are formed by those compounds who have less electronegativity difference. So they don't really make a lot of the electronegativity difference is not very high between the atoms, and that's when they form covalent bonds. Now, looking at the electron dot structures or the Lewis structures, sometimes, so it's written as Lewis, but pronounced as Louis. So these are the Lewis structure that you can draw about. There are questions sometimes asked directly on Lewis structures. So you can put carbon and you can draw four carbon electrons around them. All the crosses mean carbon electrons, all the dots mean hydrogen electrons, and you can make circles around them, forming octets. So you can see the circle around carbon as 8 electrons, and therefore octet is complete, whereas the hydrogen has duplates, and therefore hydrogen ends up giving sharing one electron, and therefore duplates are formed. If you actually look at the carbon hydrogen electrons or Lewis structures in C2H6, then we'll understand that in all of these, there is one electron each shared by hydrogen, but four electrons by carbon. One important point is that one electron each is shared between two carbon atoms, forming a single covalent bond between carbon. So you'll find that this actually tends to form C2H6 molecule, and that's called as ethane. So these are some examples of formation of electron dot structures or Lewis structures. Uh, so yes, silicon also does exhibit tetravalency. It's just that silicon cannot form as strong a bond as carbon because of its bigger size or larger size. So therefore, silicon does not exhibit catenation property. But yes, silicon also forms tetravalency. So these are some points on drawing Lewis structures. Now let's look at the characteristics of covalent compounds. Uh, all these covalent compounds, all of these molecules generally are molecular in nature. What do you mean by molecular is they would have individual molecules like Cl2 or F2, etc. If you look at other ionic compounds, like NaCl, you'll find that NaCl has an entire crystal lattice structure. So it will be completely present in blocks. But if you look at Cl2 and F2, all of these generally are in molecular state. So they are like individual molecules. So most of these would look like only molecules in nature, and they are single molecules to really say. Now, all of these covalent compounds mostly are insoluble in water. So I'm saying mostly because, in general, the principle of like attracts like works here. And water is a very polar molecule. Polar in the sense that the charge separation between two atoms, for example, in H2O, is pretty high. The oxygen has a lot of negative charge, and the hydrogen has a lot of positive charge. And therefore, with this charge separation, you'll realize that the polarity is induced, and therefore covalent compounds, because they don't have much of charge separation, are rarely soluble in water, but they are very readily soluble in benzene, kerosene, and petrol. And the reason is all of these benzene, kerosene, and petrol are actually non-polar in nature, and therefore like dissolves like, and therefore they are soluble. Of course, because of the unavailability of electrons, they are very poor conductors of electricity. So you'll realize that electrons would not be present so readily available in chlorine, fluorine, iodine, and all of these, and therefore generally they would be non-conductors of electricity. So that's some of the characteristics of covalent compounds. Of course, the number of electrons contributed by any atom is known as covalency. In other case, we just said valency. So if valency is for forming a covalent bond, then it's called as covalency, whereas valency forming an ionic bond is actually called as electrovalency or ionic valency. Okay, so now that's a quick look at the characteristics of covalent compounds, and then we'll look at allotropy in carbon. Now you'll find that allotropy, the very basic word allotropy means of different forms. So the element remains the same, but forms change. Again, there is a lot of confusion that students have between allotropes and isomers. Now, please note isomers are different structures. Allotropes are only different forms, so they are made of the same element. Allotropes is only for the element, but isotropes isomers would be mostly for molecules. So the property by which elements exist in two or more forms is basically what we call as allotropy. And because of this, their physical and some of the chemical, we have written some of the chemical, not all, because of course being the same element, not all the properties change. Only a few properties would change, chemical properties would change. So therefore, but the physical properties change very largely. I've given you two examples here. For example, in carbon, diamond is a very, very hard substance, whereas if you look at graphite, which I have shown here, so this graphite is actually used as lubricant. So on one side you have a very hard substance, on the other side you have a substance so soft that it is actually used as lubricant. And this is purely because you'll find that there is a different form that they actually connect with each other. Now, carbon exists in two allotropic forms. One is the crystalline form, and the second is the amorphous forms. A typical question asked in allotropy is, define the term allotropes and state the different allotropic forms of carbon. So in the first classification of allotropy, we mention as crystalline and amorphous. In the crystalline form, we say that there are two more, which is diamond and graphite, whereas in the amorphous forms, it is coal, charcoal, and lamp black. So all of these are basically different allotropes of carbon. And then we have fullerenes, which basically forms another class of carbon allotropes. Fullerenes actually comes under crystalline form. The first one to be identified was a C60, which we call as the Buckminster's fullerene, which has carbon atoms arranged in the shape of a football. The NCERT does not speak more on fullerenes. This could be enough for us to really define fullerenes if a question is asked on allotropy. So this is allotropy in carbon particularly. There are many other allotropes available for different other compounds, different other elements, and given a question, we can also address those. Now, formation of very large compounds is typical in carbon, and the reason is catenation, as we all know now. So, just as a point of revision, catenation basically happens to be the property in which long chains of carbon atoms are formed. So you can see that I've shown one molecule here. It just has 6 carbon atoms, but this carbon atoms can extend to a very, very long length. Sometimes to a tune of about 100 molecules or more than that, almost 2000 that are possible in some proteins. But all of these molecules are polymers. So when you form a typical polymer, you'll find that the entire carbon chain is connected to each other by covalent bonds, and this long chain formation is called as the property of catenation. So basically, we have more than 3 million carbon atoms or carbon compounds that we have now, and every year more and more carbon compounds are registered. At this number is, I'm sure, at least a couple of years old. We have much more registered this time now. Now, firstly, why is carbon showing the property of catenation? We know that the first reason is tetravalency, that its valency is 4, which is the maximum covalency that you can really have. Secondly, carbon being a very, very small atom, the size of carbon atom being very small, its bonds are very much stronger. So we realize that carbon is the first atom, in fact, having 4 valency, and therefore when it forms a tetravalency with other atoms, you will realize that the bonds that it forms is much, much stronger. So that these are the two major reasons. The third reason is, of course, it can withstand the bond strain and bond stresses. So that's another reason that carbons can be utilized to form catenation. It shows the property of catenation, or can be utilized to form long compounds. Now I've shown you 3 basic ways that carbon forms molecules. One is the long chain, branch chain, and closed ring. The point is that whenever the property of catenation is asked, it is a good idea to actually mention all of these three to show that carbons can be linked to each other in multiple ways. So these are the examples that you can write in catenation to show the linkages between carbon atoms. Right. Now, let's look at the different classifications of carbon atoms. Now, the most important class of carbon atoms is called as hydrocarbons. Please note there are other carbon molecules that are present. For example, CO2 is an oxide of carbon. CO is an oxide of carbon. We also have CCl4, which is actually a halide of carbon. So there are multiple other classes of carbon compounds, but hydrocarbons is one of the most prominent classes. And what we mean by hydrocarbons is compounds which has carbon and hydrogen as the primary atoms, forming the compound. Now, when hydrocarbons are there, there are two major groups of hydrocarbons. One is a saturated hydrocarbon, and the second is unsaturated. Saturated hydrocarbons are all of those hydrocarbons who have a single covalent bond. Please do not say they are only alkanes, or they are those atoms which either have hydrogens completely, etc. Because please note that in cycloalkanes you have two hydrogens less, although cycloalkanes are also saturated hydrocarbons. So a very simple definition of saturated hydrocarbons is to say all of them have single covalent bonds between carbons. Of course, alkanes are the most important saturated hydrocarbons, and they end up by a suffix which is ane. So we can write it as methane or ethane. I have given two examples. So when you write saturated hydrocarbons, always write the definition and write both of these examples, or maybe one example should be okay. So that's the saturated hydrocarbons. What are unsaturated hydrocarbons is when you have more than one bond between carbon atoms. So yeah. So when you have hydrocarbons with double and triple covalent bonds between carbon atoms, we call them as unsaturated carbon atoms. Uh, Triple bond is the maximum that carbons can form between themselves. And for that matter, any two atoms can form between themselves. An example is an alkene, where a double covalent bond is present between two carbon atoms and it ends with an ene. So you'll find that ethene or propene is a classic example of an unsaturated hydrocarbon. At the same time, an ethyne, where there is a triple bond that is put between two carbons, ethyne or propyne will be present. So you'll find that two carbon atoms having triple bond will end up with an ine. So these are the two examples of unsaturated carbon atoms. Now, let's look at isomerism. We just spoke about allotropism. Now we'll look at isomerism. So whenever carbon compounds have the same molecular formula, I hope you are able to read this. If you don't find it legible, you can always let me know. But I'll read it for you. So carbon compounds having the same molecular formula but different structural formula are called as isomers. And this property is called as isomerism. Okay, so I've shown you an example. This is a butane with 4 carbon atoms. They're all arranged in a straight chain here, as you can see. And here is a butane where you have 3 carbon atoms in a straight chain and the 4th carbon atom, branched. So the molecular formula, if you see both of them, is actually C4H10. You'll find that there are 10 carbon atoms, 4 at the top, 4 at the bottom, and 2 on the side. If you look at this, you'll also find that the hydrogen atoms are also 10 here. So both of them actually have the same molecular formula, which is C4H10, but their structures are completely different. So this is actually what we call as isomers. Having different structural formula but same molecular formula. When if another example is asked, or they ask you to write the different isomers for pentane, you'll find that for pentane there are 3 isomers possible. So one is called as N-pentane, which is a straight chain compound. The second one is called as isopentane, where only one branch is possible. So this is an iso compound, isopentane. And then we have a neopentane, where there are 2 branching on the same central carbon. So this carbon has 4 carbons attached to it. So iso and neo. Isopentane, neopentane. These are the 3 isomers of pentane that are possible. Now, let's look at isomerism. Once we have seen isomerism, let's look at functional groups. The functional groups are of multiple types. So some of the functional groups are generally pretty simple in nature. For example, chlorine, bromine, iodine. So what's a functional group really to understand? So an atom or a group of atoms which decides the properties of a carbon compound is called as a functional group. So by its very words, we know that it defines the function, ideally. But in our sense, in the language of chemistry, to that function we'll call it as either chemical property or physical property. So an atom or a group of atoms which decide the properties of the compound, carbon compound, is called as functional groups. The most easiest or the common functional group is our halide. So you'll realize that the halides are the ones that actually would be forming, the halo groups will be forming the easiest of the functional groups. Now whenever functional groups are mentioned, they generally are written either as chloro or bromo ethane. Firstly, this functional group halides is generally written as haloethane or haloalkane in general. So you'll realize that if I have to write it as chlorine with methyl group, I will call that as chloromethane. Okay, so that's the way that you can actually work out on the functional groups. You can name the functional groups. Now if you look at the alcohols, in alcohols we will use a suffix all, and we'll shortly look at all the suffixes of functional groups in nomenclature. But so Kritika is asking, how do you define homologous series? Yeah, I'm just coming there, Kritika, in a minute. So alcohols are ones which has the OH group as the functional group. Aldehydes are the ones which has the CHO group. Please note how the bonding is. So carbon is directly bonded to hydrogen and then doubly bonded to an oxygen. This is an aldehyde. And when there is no hydrogen attached, please note, to the carbon, you don't need a hydrogen. You can only attach it to carbon. This is called as a ketonic group. So remember the difference. One has the hydrogen, the second has the ketone group. In carboxylic acid, the carbon is attached to two oxygen atoms only. Oxygen further is attached to hydrogen. So that is the carboxylic group. Please remember the carboxylic group. The ketone group, aldehyde group, and carboxylic group are one of the most uh, uh, important functional groups that we need to know. Now, going back to other functional groups, I'm going to just make a fleeting mention of two more functional groups for you. We have C, O, and C. This functional group is called as ether. It's called as ether. And C, double bond O, where carbon is attached to one oxygen and this carbon is attached to another carbon, this is called as an ester. So ether and ester, please do not forget this. Remember that ethers have only one oxygen. So you can remember two, and you can remember so with a double O. So with a double O. So esters means with double oxygen and ethers mean with one oxygen. Okay. So that's an easy way to remember ethers. So E to her, or that's also we sometimes say that E to her, which means that it has only one oxygen, and iso her. So so that's, so the very word so, the way we pronounce it, that's one way to remember that esters have two oxygens with them. So that's a quick note on functional groups. Now let's understand what is a homologous series. So to answer even Kritika's question, what is a homologous series? So homologous series is a group of carbon compounds having similar structures, similar chemical properties, and whose successive members differ by CH2. One of the very, very major mistakes that people do is same chemical properties. They write this as same chemical properties. Absolutely wrong. Absolutely wrong. Or same physical properties, also wrong. Okay, same physical properties also wrong. The properties are similar. Now because of the exceptions, please understand that as it goes from smaller carbon to larger carbons, as the weight, as the molecular weight increases, the physical properties definitely change and substantially change, while most of the chemical properties remain the same. Same means exactly identical. As they become very high, for example, when you end up getting to, for example, C10H22, you will realize that the chemical properties also slightly vary. So therefore we say that as you go larger and larger in the molecule, you'll find that similar word is used, which is a very important word. Similar structures and similar chemical properties is what we use. In fact, you can also very easily mention whose physical properties are either incrementing or decreasing by a regular interval. That is also a very good way to say that how the properties change in a homologous series. So that's a quick way to look at homologous series and understand what they are. So I've given you one homologous series here, which is the alkanes. So you'll realize that methane, ethane, propane, butane, pentane, all are the homologous series for alkane. The general formula for this is CnH2n plus 2. And one quick note is sometimes you might have to derive the general formula for homologous series, and all you have to do is look at the sequence and try to put in values at n and try to derive this. So whether it is CnH2n plus 2 or simply CnH2n or CnH2n minus 2, all of that would be possible if you just simply put in values and check what formula is true, right? So that's one of the ways of really writing homologous series and mentioning a general formula. This is called as the general formula or the molecular formula for a homologous series. Again, another spelling mistake that generally people I see is they write it as GUS. No, it is GOUS. So this is another mistake that I've found recently that people keep on making. So beware of these. Whenever a question of homologous series is asked, please write your definition. Please write general formula of one homologous series. Please give an example. Write at least four members, not three, but four, because four establishes the fact of homologous series pretty strongly. So please write four. I've given you five. If you get time, it's more than happy to write five. Also mention if it is a 4 mark or 3 marker question. Generally a 3 marker question, and it's just a quick point that you have to write. You can write two more points now, where you can say that the chemical properties are similar and physical properties differ by regular intervals, right? So they actually increase or decrease by regular intervals. To give you an example, the boiling point and the melting points, they increase by a regular interval. But if you look at, for example, molecular weight also increases. Let me see. So these properties increase at regular intervals. So you can mention that how physical properties increase or decrease at regular intervals. So that's homologous series and for us, and we can always mention them in the texts. Now, a deeper look at alkenes we have definitely seen as alkanes. But if we have to look at the homologous series of alkenes, of course, there is no methane possible, but there is ethene, which is the lowest member of the homologous series is possible. The general formula, as I mentioned, is CnH2n, and their names always end with an ene. So you'll find that ethene, propene, butene, and pentene are the first four members. As I said, you have to write minimum four members when you write a whole homologous series. If you get time, it's always good to really draw the structures as well. Please note, in CBSE, in your board exams, try to write in as much as possible, keeping in mind the time that you have. Okay, so of course, sometimes this goes overboard and people write so much that they don't get time to write the entire paper. So it's always a good idea to mention things in point wise, but also give more points. So sometimes if one point is wrong, or the teacher or the examiner is not happy with your answer for one typical point, he can always give an additional mark or a half a mark with some additional point that you have written. So that's a good idea. Of course, if you don't know any answer for any question, I strongly recommend that you at least write what you know. Sometimes it is quite often in the board exams that just for the way that you have analyzed the answer, for example, the way that you have written the given or you have written the units for the question, you might end up getting a mark or two. So please always attempt all the questions as far as possible to the best of your knowledge, but do not leave anything blank. Do not Also read the question carefully. If there are 3 or 4 bits, it is mandatory to write all the 3 or 4 bits. Today we are at the last chapter of chemistry. We have already done chapter 1, chapter 2, chapter 3, and chapter 5. I strongly recommend that you remember all of these points that I'm telling you at this chapter. It will help you in scoring the max possible. Okay. Now, so this is what we have done with alkenes. Now let's go to the next. Alkynes. Again, I have given you 3 here. So in alkynes, you'll realize that the general formula is CnH2n minus 2, and you'll realize that the lowest member is an acetylene or ethyne, propyne, and butane. You can also draw the structure for ethyne, propyne, and butane. All of them can have 3 triple bonds. Please note to draw all the hydrogens for all the other carbons if you're drawing structures. Very, very important point to have. Very important point to have actually the maximum bonds that you can see. Okay, so these are a few things that you can actually work out with. So these are homologous series of alkane, alkene, and alkynes. Now let's go to nomenclature, one of the most important topics that of carbon and its compounds. Most people need practice on this. So today I'm going to talk about all the different rules of nomenclature as we go forward. The nomenclature system is the system given by IUPAC, which is the International Union of Pure and Applied Chemistry. This is the one who established the system and gave certain rules so that we can have a common language across the geographies to have communication between chemistry names of compounds. Now, we will refer to the names derived from this system as systematic nomenclature or the IUPAC nomenclature, generally shown in blue. But sometimes there are also additional names which are very common that are used, and I've tried to show all of those names in red. For example, isopentane or neopentane are common names. They are not IUPAC names, but they are very much used in our text. In fact, IUPAC also accepts them. It's not given by IUPAC, but it accepts if you use those nomenclature while naming. So that I've tried to show you in red in the following examples. And a compound may have more than one name, but it will always have only one and one compound specified. So a name must specify only one compound. One name cannot specify two compounds. So if you want to look at the analogy, what I'm trying to say is names. You can have for one compound you can have two names, but the reverse is not true. So the reverse, one compound, so if you say that the name, whatever name you take, the name should only give you one compound. But a compound can have two names, but names cannot have two compounds. So this is the way that you can actually represent it through a relationship or a set method. Now let's look at how do you really name hydrocarbons using the IUPAC system. So this is actually a series of prefixes that are used for the root. So there is something called as a root that we use, and the prefixes and suffixes are added to this root so that we get a final name. Now, what are the roots? Methyl, ethyl, propyl, meth, eth, prop, but, pent, hex, sept, oct, non, dec. These are the roots of naming carbon compounds. These roots are for the number of carbons that are used. For example, if there are 8 carbons used, you will say it as oct. If there are 4 carbons used, you will call it as but. If there are 6 carbons, it is hex. So depending on the number of carbons, you have to choose the root. Remember these roots pretty well. I still have seen students who are confused with these roots. These roots are still not perfect for them. I strongly recommend that you remember these roots and have a strong hold on knowing these roots. So these are the roots. I'm going to keep this slide with you. Any point you feel that these roots have to be memorized, just scroll back to this point of the recording. Anyways, this recording is there on the YouTube. Come back to this recording and you'll realize that you'd be able to memorize this. Now, how do we really name some alkyl groups, right? So if there is a CH3, just there is CH3 in the molecule, then that is what we'll call as the methyl group. And when there is two CH3, please note, methyl is something that is one hydrogen less than methane, which is an alkane. Ethyl is something that is one hydrogen less than an ethane. So anytime when you take out one hydrogen, you write ethyl and methyl. Please do not forget that these are not methine. So the L and Ne, do not mix those. Methyls are substituent groups, but methine and ethyne are compounds. They are a complete compound. These substituent groups are partial compounds. There is something they are attached to the primary compound. So methyl, ethyl, propyl, isopropyl, butyl, isobutyl, sec-butyl. Now I'm going to tell you the definitions of iso and sec. Whenever there are two methyl groups attached to carbon, please note, whenever there are two methyl groups, we call that as an iso molecule or iso substituent rather. Now, whenever there is a methyl and an ethyl group, please note, methyl and an ethyl group, it is called as a sec or secondary butyl or sec, only sec. Okay, I can give you one more example. You can have this molecule also present here. There is a methyl and a ethyl group. This is an isopentyl because there are 5 carbon atoms. So this is an sorry, this is a sec pentyl. I'm sorry, please note, it is a sec pentyl because there is an ethyl and a methyl group attached to carbon. It's called a sec pentyl. And when there are 3 methyl groups attached to one carbon, it is tert. This is a normal pentyl, and you'll realize that isopentyl again has two methyl groups attached to carbon. So two methyl groups, a quick formula I'm going to give you, two methyl groups means iso, and a methyl plus one methyl plus one ethyl, okay, one methyl plus one ethyl is nothing but a sec, okay, sec compound. And there are three methyls attached. It is called as a tert compound. And the neo means there has to be a 4-degree carbon. Okay, so neo is this group where one carbon has attached to four methyl groups. So, or four carbon atoms. So four carbon atom attachment is called as a neo. You can write this down as a formula for yourself, and this will be, this is something that you have to remember. You have to really be with you. So these are some nomenclature, some common alkyl groups that you can always refer to. Okay, you can always come back to this video and see if any points that you feel are you might have missed out or you need to remember. You can come back here and connect to it. Now, typically an alkyl group is always represented by R. So all of these compounds that you see on the page can sometimes always be written by a simple R, just to show that, okay, there is an alkyl group present in it. So this is the way to represent substituents on the root. Now let's look at how we go by the rules. Now alkyl substituent group names are always combined with the alkane name for the longest straight chain. So we have to always firstly identify the longest straight chain compound. So for example, you'll realize that here there are about 7 carbon atoms, and so that is an heptane. Please note here there are always these substituents, and therefore although there are 7 carbon atoms, the longest chain is only sorry, there are in fact 1 2 3 4 5 6 and 7. So there are 7 carbon atoms. So although this is an isoheptane in common name, if you write the IUPAC name, you will find that we write it in terms of hexane. So hexane is what we choose because the longest chain is only of 6 carbon atoms. The total number of carbons is 7, but that is only applicable to common name, not applicable to IUPAC. Now, let's take another example. Here, the longest chain is of 6 carbon atoms, and there is one methyl on it. Here, the methyl was on the second carbon atom. So this was 2-methyl hexane. Now, this numbering we did because we need the lowest number. We are quickly going to come to that point as well, how to do the numbering. But the point that I'm making here is only of one point, which is check the longest carbon chain. Now, if this has to be this, I had to write it in the common nomenclature. Since there is an methyl and an ethyl group, this is called as sec heptane. It can also be called as sec heptane. Okay, so but this is a common name, or a common name that you can have. It's not an IUPAC name. So therefore, you'll find that the IUPAC name will be still 3-methyl heptane, 3-methyl hexane. Sorry. So note these compounds all have the formula C7H16, and therefore they're all isomers. So all of them have the same formula, but they are different isomers. Their common names do not change. Their common names still remain heptane, isoheptane, and sec-heptane, as I showed you. But their IUPAC names definitely change. This is simply an heptane in IUPAC. This is a 2-methyl hexane, and this is a 3-methyl hexane. So remember the longest chain rule that I have just mentioned so far. So determine the longest chain of parent compound. We just saw how to do that. Second is cite the name of the substituent before the name of the parent hydrocarbon along with the number 2 carbon to which it is attached. This is the second rule that we have to follow. For example, here you will find that in this compound, the longest chain is of an octane. Please note this is the longest chain. So if I have to really draw it for you, I would choose this as the longest chain. And in this chain, I'm going to decrease the transparency a bit. Yeah. So you'll realize that in this longest chain, there are 2 substituents on it. And therefore, when you write octane, before octane is what you really write, either methyl or isopropyl. So this is an isopropyl one. So in isopropyl, you realize that it is written in the form because there are 2 methyl groups. So this compound can also be written as isopropyl. As I mentioned, isopropyl is commonly accepted in IUPAC. Now the numbering, which is the second rule that we'll come to, is it has to have the smallest numbers possible. So you'll realize that methyl can get a 2 here, and this can get a 5. But if you look from the other end, you'll find that you will end up getting 1 2 3 4, and this will be actually at 5 6 7. So instead of taking a 4 comma 7, we would be very happy to take a 2 comma 5. So this is the second rule that I'm mentioning, and the second rule says that the numbering should be lowest to the substituents. So the substituent should always get the lowest number as much as possible. So this is the numbering rule, and the way that we write it. Now the next is, as I mentioned, the number in the direction that gives the lower number for the lowest number substituent, and substituents are listed also in alphabetical order, neglecting the prefixes di, tri, tetra, etc. I've said this time and again. So if there are multiple suffixes, multiple methyl, ethyl, you do not have to take d, t, t. You have to simply take methyl, etc. So if you really see that here we have three ethyl groups. One is this one, second is this, and third is this. So you'll realize that in all of these three, you simply go by the alphabetical rules. So you'll find, in fact, the first one is that you'll always choose the lowest number. So lowest number beats the alphabetical rule. So if you get lowest number from one side, you go by that. But if the numbering is the same from both the sides, then you will go by the alphabetical rule. So you'll find that here there is a third carbon each, there is an ethyl group. At the sixth carbon, there is an ethyl group. And at the seventh carbon, there is a methyl group. So you'll write this as 3336 trimethyl. Please note the word tri. So you have to mention for every substituent that is there on the carbon atom, you have to have at least one number for it. Had it been tetramethyl, you would have to write here four numbers. Four numbers are important. And of course, with methyl, you'll realize that there is only one, so therefore you have to write 1 7. Okay, 7 methyl. So that's decane, because there are 10 carbon atoms in the longest chain. So we all know these rules, we are just revising it, so that you are very thorough with it. Now when both the directions yield the same lower number for the lowest substituent, select the direction that yields lower number for the next lower substituent. For example, in this scenario, you will find that from both the directions you have the same number, which is 2 2 for methane. So you will realize methyl, or the methyl group, you'll realize that we will still go from this side, because the second substituent is getting lowest number if I go from this side. So once methyl are taken care of, I have to think about the second substituent, and therefore I would choose this carbon as 2 and this carbon as 1, and I write it as 2 6 dimethyl 3 ethyl. And while writing, I'm writing in the alphabetical order. Please note that E comes first and M comes later, although D is less than E, or D is alphabetically senior, or earlier than E, but D is not to be considered. D is not to be considered. We only have to consider ethyl and methyl. Please do not write it as 5 ethyl 2 6 dimethyl. No, because 3 is lesser than 5. So this is a quick method to, sorry, this is a quick method to really do the nomenclature. Yeah, so we just saw this. Now, some more rules. If the same substituents are obtained in either direction, number in direction giving lowest number to the first named substituent. So let's like we'll look at one of the examples. And if a compound has two or more chains of the same length, parent hydrocarbon is chain with greatest number of substituents. Okay, so please check here. I've just mentioned an example for you. So in this scenario, this also has 6, and this also has 6. But if you go by this chain, you'll find that there are two substituents on it, which means two branching on the main chain. If I go by this way, there is only one branching on the main chain. So then I will not choose this. I will choose this with the two substituents. Okay. So 3 ethyl 2 methyl hexane. Why 3? Please note it is on the third carbon. Also, please note I have started numbering from here, so it will always be 2 methyl, and therefore it really works pretty well on this. Now that's a quick a glimpse of all the what should I say, the rules of nomenclature. Only these rules are important for you to go forward, and you'll realize that these rules will be sufficient for you to really answer all the questions in the board. So these are the rules for nomenclature of all the straight chain, all the alkane without the functional groups. A quick look at the functional group nomenclatures. If there is a functional group, and groups have unique suffixes, then this is how you should name it. So for aldehydes, you will write it as all. So for example, ethanol, methanol, propanol. For aldehydes, you will write it with an al, ethanol, methanol, propanol. For ketones, you'll write it as on or one, which is methane. So the lowest ketone that you'll have is actually propanone. So propanone, butanone, pentanone, and that's how you'll name ketones. Acids are with an oic acid, okay, with an oic acid. So you write this as ethanoic acid, butanoic acid, propanoic acid. Esters is not really important, but I'm just giving all these three. So don't worry about esters, amides, and amines, but you simply, for example, write this as ethanamide, propanamide. Amines can also be written as ethanamine, propanamine, butanamine, so on and so forth. And ethers can be written as ethoxy with a prefix. Bother less about amides, amines, and ethers, esters, but these four are very important for you, and that's where you can really get a question or two. You'll also realize that fluoro, chloro, bromo, and iodo are also written before as a prefix. This is the only one which is different. Please note, all of these were suffixes. Only this one is a prefix. Only this one is a prefix in IUPAC. So, at any point of time, whenever there is a functional group, always give importance to functional group first over substituents, over double bonds, over triple bonds, or anything else, except for the halogens. Halogens are not given any preference at all. They actually come after double and triple bonds also. But for all the other functional groups except halogens, always give a preference. Just remember these three rules. You can go over these rules once again, as I always said. You can just rewind this video at any point of time and go through these rules, and you'll realize how to name them. So this actually completes the nomenclature. This should be suffice for your nomenclature rules. I don't think so that there would be a direct question as to state the rules for nomenclature, but they definitely would give you a molecule and ask you to name it, which is where you need to remember the rules, and you can always attempt that. Now this brings us to the the last major component, and there are some smaller components as well, but the major component of today's chapter, which is the chemical properties of carbon compounds. There are specific chemical properties that are very important for you in this chapter, and I have tried to keep them in one single array. I have tried to align them. The reactions that are important to you is combustion, oxidation, addition, and substitution reactions. So only four of them are very important. The first one is combustion. Combustion simply means heating or simply burning in oxygen. Anything that you burn in oxygen, you'll realize that you'll end up getting CO2, which is the oxide of carbon. You also end up getting CO, but that is when incomplete combustion. So whenever there is a complete combustion, always CO2 will be formed. So the carbon compounds burn in oxygen to form water and carbon dioxide. When it is only carbon, you'll end up getting CO2 plus heat plus light. But when there is a methane or an alkane here, you'll find that alkane plus oxygen will end up giving you H2O plus CO2. So carbon compounds, mostly hydrocarbons, is what I would suggest is what actually end up giving water and CO2. But if you have other carbon compounds like alcohols, you will find that the oxygen ratios changes slightly, but it still ends up giving you water plus CO2. Please note to balance all the reactions at each point of time. And it's a good idea to mention an arrow upward saying that release of CO2 as the molecules actually, get combusted or simply burn. So this is the combustion reaction. Complete combustions give this. Incomplete combustion gives you carbon monoxide. So you can write that as CH4 plus oxygen giving CO plus H2O. Now, in this scenario, you'll realize that, let me see. So you need two of hydrogen. So you basically have 2 plus 1, 3, 3 by 2. So you'll get here 2, you'll get here 3, here you will get another 2, and here you will get 4. That is how you can balance this reaction. So it is 2, 3, 2, and 4. That will end up giving you an incomplete combustion with CO molecule on the formed in incomplete combustions. Now, also remember one more property that is very typical that is asked is in complete combustion, you will always have a blue colored flame. Whereas in incomplete combustion, you will either have a yellow or reddish yellow or orange colored flames. So blue and yellow or orange yellow is something that you have to remember. So that's your combustion reaction. Now let's look at the oxidation reaction. The oxidation basically means addition of oxygen in the molecule. So for example, if you oxidize alcohols, you'll end up getting ethanoic acid. These go through two intermediates where it does not stop, but in between two intermediates are formed, and those are, so alcohols basically end up going to aldehydes and ketones. So aldehydes and ketones are mentioned, and apart from aldehydes and ketones, it further goes to acids. Okay, so acids is the highest oxidation state, so it cannot get oxidized any further. But aldehydes and ketones can definitely get oxidized further, and that can also happen. So you'll realize that alcohols to acid, aldehyde ketones to acids is how the the reaction proceeds. What are the reagents that are used? Alkaline KMnO4 or acidic K2Cr2O7. Both of these are used, and a small amount of heat is given to end up giving ethanoic acid, which is also called as acetic acid. So the reagents alkaline KMnO4 and K2Cr2O4 are called as oxidizing reagents or oxidizing agents, and they are nothing but potassium permanganate and chromic oxide. Okay, chromium oxide. So potassium chromium oxide. So or chromate, potassium chromate. That's also how we call it. Okay. So potassium chromate and potassium dichromate also. Chromate is with one chromium atom, and dichromate is with two chromium atom. So potassium dichromate or potassium permanganate is what really gives these oxygens for oxidation reaction. Please remember the oxidation reaction directly. All that has been there in the PPT can be directly written as answers. I've tried to model this PPT in the way that you can write your model answers directly. So this is one quick mechanism of one quick method of writing the chemical reactions. And then we have addition reactions, where you will find that unsaturated hydrocarbons undergo addition with hydrogen majorly in presence of nickel or platinum palladium as catalyst to form saturated hydrocarbons. So you'll realize that, for example, C2H4, which is nothing but your ethene, it has a molecular structure like this. It undergoes an addition with hydrogen in the presence of nickel or platinum or palladium to end up giving you C2H6, which is your alkane. So ethene undergoes addition reaction with hydrogens to form ethane in presence of nickel or palladium as catalyst. So that's a quick way to do that. The second is addition of hydrogens to unsaturated hydrocarbons to form saturated hydrocarbons is called as hydrogenation. So this reaction is also called as hydrogenation. Hydrogenation simply means that you are adding hydrogen to the molecule. So that's hydrogenation. Hydrogenation is also used to convert unsaturated oils and fats to saturated oils and fats. Okay, so that's also one of the ways where saturation can be brought in. And then there is a substitution reaction. Substitution reaction by its very name means that you are going to substitute one from the other. So here we are substituting the hydrogens from with chlorine. Okay, so you will realize that in the first reaction you will find that only one chlorine is substituted. This is called as chloromethane. And then further another hydrogen is substituted. You will realize that we call this a dichloromethane. And then one more hydrogen gives you a chloroform, which is also called as trichloromethane. And then you end up getting carbon tetrachloride. So from a hydrocarbon, now you have got a carbon tetrahalide or carbon tetrachloride in this situation. So this is a substitution reaction. So addition, substitution, combustion, and oxidation are the four reactions that are pretty important in your syllabus, which I have all mentioned here. All these four reactions should be memorized or should be known, and which should be practiced pretty well. Now, some important compounds that are also important in the syllabus is basically firstly ethanol. And a common question is asked is how do you differentiate between ethanol and carboxylic acid? Now, carboxylic acid being acid, you can simply put in either a metal, and you'll find that hydrogen gas is released. Whereas in ethanol, hydrogen gas will be released only with sodium. Okay, so both of these are shows in fact, you can also say that you can put a base, for example, acids, especially acetic acid reacts very easily with CaOH, with NaOH, or even with CaOH twice, which is a weak base. Then there is another thing that you can do is you can use soda lime so that it gives CO2. CO2 is given out by acetic acid when you use soda lime. So that's another way to really know difference between ethanol and acetic acid or ethanoic acid. But just to look at the properties, ethanol is a colorless liquid and it has a very pleasant smell and a burning taste. It's also soluble in water. Now, ethanol reacts with sodium to form sodium hydroxide and hydrogen. So you'll end up getting C2H5ONA. and H2. Ethanol also reacts with hot concentrated H2SO4 to form ethene and water. So this is a dehydration reaction. Please note that this is also called as dehydration reaction. So what does the dehydration means? That you are basically taking out an H2O. So minus H2O. Whenever you remove H2O from the solution, you will realize that it's called as a dehydration reaction. So that's dehydration for us. And then some of the uses of ethanol is basically it's used for making alcoholic drinks. It's used as a solvent. It's also used for making medicines like tincture iodine, cough syrups, or tonics. So ethanol is a very crucial component to make a lot of drugs which are basically for human benefit, medical drugs, clinical drugs. So all of those really help in formation of compounds which are necessary for life sustenance. So that's ethanol. So remember, whenever a compound ethanol is given, you have to write its structure, you have to write its IUPAC name, which is ethanol. Then you have to write its properties if it is asked, both physical and chemical. I've given you both physical properties as well as two chemical properties. And then you have to really write the reactions for this. Please do not forget to write the reactions with a complete balance form. And the last is that you write its uses. So all of these together would fetch you 3 marks. Okay, all of them put together will fetch you 3 marks. Mind this, most of these are generally for half a mark. So a 3 marker will need all of these 5 points to be mentioned. If it is a 5 marker, you will need to give the reactions and elaborate them with one more sentence each. So that's the way to write some special compounds, especially ethanol. Now let's look at the second special compound, which is acetic acid, which is in our syllabus. So ethanoic acid or acetic acid is again a colorless liquid with a pungent smell and sour taste. It is soluble in water, very much like ethanol, and the solution is 5 to 8% ethanoic acid, also called as vinegar, commonly found in households. Now, the another important reaction that is mentioned in our syllabus is actually the esterification reaction. Now, esterification reaction means where esters are formed, where esters are formed. So in esters, you will find that your acetic acid actually reacts with your alcohol to end up giving CS3CO C2H5. So concentrated H2SO4 ends up giving you esters, basically dehydrating. So OH is taken from your. Please note that I've always said this to you. It is the acetic acid which ends up giving you OH, okay, and the alcohols ends up giving you hydrogen. So please note this. So the hydrogen NO and C2H5, the dehydration happens with OH being given from the acetic acid. This was a common mistake that most students had done in the previous exam also, that I checked, that OH is given from the acid and H is given from the alcohol. People generally take H from acid and OH, but that's not true in esterification reaction. So please note how do you write the reaction. If you're doubtful, don't write this. Okay, please don't write this circling on all. But if you're confident, you can write this HOH, and you would write then the molecule as CH3COOC2H5, which is an ester. Now, this is named as ethyl acetate. Okay, so you generally take whatever is after oxygen as the alkyl group and something that is before as the O8. So this is ethyl acetate, and that's ester. So carboxylic acid and alcohol form ester. This reaction is called as esterification. And then you have saponification reaction. So this is another very important reaction mentioned under these special molecules. So the saponification reaction is the one when an ester basically reacts with sodium hydroxide, and it gives you a sodium salt of carboxylic acid, and the parent alcohols are formed back. Okay, so this reaction is called as a saponification reaction. You will end up getting parent acid, but this is a salt of the acid. So acids cannot remain by themselves because there is a base present around the solution, so they end up forming a salt. So you'll find that you will end up getting sodium acetate and you'll end up getting C2H5. So this is an alcohol and the salt of the parent acid. Now, the next one is you will end up getting ethanoic. The reaction is pretty simple. An acid-base reaction, you will find that H2O is formed. So with acids, you end up getting salt and water, but with an alcohol, you'll end up getting hydrogen gas. So please note this difference between ethanol and ethanoic acid, as I mentioned to you. Now, ethanoic acid reacts with carbonates and hydrocarbonates to give CO2. This is also another test that you can mention for distinguishing ethanol and ethanoic acid. Ethanoic acid with carbonates and bicarbonates end up giving CO2, but alcohols do not end up giving any CO2. So these are the quick points on which you can actually look at to understand the different reactions of ethanoic acid. So now that brings us to probably the last topic of today's chapter. And after this, I really encourage, if you have any questions, now is the time that you can post these questions so I can address them. Else, we are just at the end of today's session in understanding what are the different aspects of, or how do we really write the answers for different questions today. So, soaps and detergents are basically basically a topic of importance in carbon and its compounds. Soaps are long chain sodium and potassium salts of carboxylic acids, whereas detergents are long chain calcium and magnesium salts of carboxylic acid. So please note this sodium and potassium word. So soaps, sorry. So if you sorry so if you really see that sodium and potassium salts are the ones that are present in soaps, and for example, sodium stearate, is one of the soaps. You see that it has the carbon will be generally from 16 carbons to about 20 carbons, and so this is one typical stearate molecule that we have, where you will find that the salt of a long chain, which is C17, in fact it is 18 carbons. The acid, long chain acid, is present, and this it's salt with sodium hydroxide is present. Now, the structure of a soap is basically formed by two parts. One is the hydrophilic and hydrophobic. So this is water attracting, which means this is the hydrophilic part. Hydrophilic means water loving, and then you have what the long chain repelling, which is an hydrophobic part. So you'll realize that both of them actually are separate, or they behave separately rather. This is a very long chain, and then there is a small a molecular interaction at the end of it, like the head of the, and this is the tail of the molecule. So now how the cleansing action happens. This is a cleansing action of soap, which is a typical question asked in CBSE for quite many years. So they ask you explain the cleansing action of soap. So basically, when soap is dissolved in water, we are going to look at this diagram in the next slide in much more detail. But for the time being, when a soap is dissolved in water, it forms spherical structures called as micelles. Now, each micelle basically ends up forming soap molecules. Why? Because they arrange themselves radially. Now, radial is again another good word to be used, because you'll find that there are spheres that are formed. So they are arranged radially, such that the hydrocarbon part is towards the center, because it is the one that dissolves the dirt. Okay, so the dirt, whatever is present here, whether it is grease or oil, they are hydrocarbon in nature, and therefore they are attracted by the hydrocarbons themselves from the tails of the molecule or the micelles. And the ionic part is attracted towards the outside because it is polar, and therefore it will try to go towards where water is going. And this SC part dissolves the dirt or oil. So basically you form an enclosure for the dirt, oil or grease, and it forms an emulsion at the center of the micelles, right? So an emulsion is when liquids are dissolving inside liquids, and these emulsions can then be washed away by water. Okay, so you'll find that these emulsions further, once they are washed out, with their washing, the dirt particle is also taken out. So these are the cleansing action of soap. You'll find that in both the waters, the dirt, here there is no dirt, but here there is a dirt, and the soap molecule is formed, and micelle has entrapped the dirt particle, and here there is only a micelle that has been shown. So that's how the cleansing action of soap happens. Now let's look at the figure of that is necessary that you should draw. That you'll find that here there is a soap molecule very clearly shown, a soap micelle, and here you will find that there is a dirt molecule that is seen, and with this dirt molecule you'll find that the soap micelles are dissolving the dirt molecule with them, and then there are hydrophilic parts which are outside, which are basically flowing with water. And you'll realize that as water is gushed in, then it basically pulls out the dirt particle from the fabric, or from the wherever it is stuck to, so that the cleansing action happens. So these two figures can be pretty well drawn, standard figures right from NCERT, and you can actually show the cleansing action. So the figures also carry a lot of weightage. I'm going to share some important points of answer writing at the end of this session today, and we can then, that's the point when we can discuss more about it. So this is the soap action or the cleansing action of soap. Let's look at detergents, the last slide for today. You'll find that detergents are long chains of salts of sulfonic acids. Sometimes there are also calcium and magnesium salts, is what we really mentioned, but they are generally of sulfonic acids. So you can very well write sulfonic acids in the solution. Soaps do not wash well with hard water. Okay, so hard water is kind of a problem for soaps because it forms insoluble precipitates of calcium and magnesium, right? So because calcium and magnesium present in hard water, they basically replace the sodium and potassium. Because sodium and potassium are very reactive, so they will end up getting forming any ions that are possible, but calcium and magnesium cannot remain in the solution, so they will get attached to the salt form and they will precipitate out. Because sodium and magnesium being more soluble, they will kick out the calcium and magnesium out of the solution. So the salt that came in with sodium is now attached to calcium and precipitated out. So in hard water, the soaps form insoluble precipitates of calcium and magnesium, and therefore they are very less effective in hard water. But if you look at detergents are very supportive of hard water because they do not form insoluble precipitates, because they themselves contain magnesium and calcium salts. Also they contain sulfonic acid, ions as well. So calcium and magnesium remain in the ionic form, which can be washed out. So detergents are effective even in the hard water. Question that has been asked time and again, and I have given you 4 points of difference also. So soaps are sodium salts of sodium, or you can also write as potassium salts of fatty acids, whereas detergents are sodium salts of sulfonic acids. You can also write calcium salts of sulfonic acids. Both are okay. But sulfonic acid is the most important one, please do not miss out. Therefore I've explicitly mentioned it here. Then soaps clean in soft water but do not clean in hard water. Detergents clean well both in soft and hard water. Soaps do not clean as well as detergents because of their limitations of solubility. Detergents clean better than soaps. So you'll realize that detergents also have ability to clean in hard and soft water. So when we say clean better, it means that the ability to take out dirt from the solution is much higher for detergents, and the ability to take out dirt is limited when we speak about soaps. So that's the difference between soaps and detergents. Now you'll realize that soaps are also biodegradable and they do not cause any pollution. Now when you say biodegradable, it simply means that they can be decomposed into smaller molecules, and the normal organic action can be carried out. But detergents, because it is an inorganic compound, because there is a sulfonic compound involved in it, you'll find that there cannot be degradation further. So as it can does not really go and break down further, you'll find that detergents are non biodegradable, or basically they cause pollution. So these are the 4 points of difference that you can always mention, and it can actually help you in writing the differentiation between soaps and detergents. Now that's the difference between soaps and detergents, as I mentioned to you. Another quick topic. So what we'll do is, this actually brings to the end of the slides. I'm going to quickly revise the entire chapter for you in the next minute or so, minute or 2 minutes. I would like you guys to now post any of your doubts. Post this revision. I will tell you the important points that you should remember while writing answers. I've already mentioned that in the presentation, a few of them, but anything that's remaining, I'll try and address those. So today we saw this entire chapter in the following subparts. So starting from the beginning, you'll realize that we saw the occurrence of carbon atoms, which whether it's in the uh, uh, you know Earth or it's in the atmosphere. So, and then we have seen what are the different types of bondings that are there. Majorly covalent bond is what we have really looked in deeper. We have seen why carbon forms covalent bonds. Its electronic configuration has to be written. Valency, difference between valency and valence electrons is what we have seen. We've also seen how covalent bonds are formed. how to write Lewis structures. We have seen single covalent bond, double covalent bond, and triple covalent bonds. There are maximum covalent bonds that you can form is triple between two atoms which are neighboring to each other. So only three bonds can be formed maximum, which is like for nitrogen. Even carbon form three bonds. So we have seen how double, triple, and single bonds are formed. We have seen the Lewis structures. Now we have seen how to really share the electrons, how to really write Lewis structures. So these are the Lewis structures that you can write. Please note that here, because I could use coloration, I have been able to share them in different colors, but for you, you'll have to use different symbols. So symbols are going to be critical if you have to write Lewis structures. When you write electron dot structures, it is a good idea to actually mention circles. Sometimes people just leave by writing the electrons, which is also okay, but drawing circles gives a more effectiveness to it. Please note how the circles are drawn. Each one of them is being seen to either complete a duplicate or an octet. They are not left behind. So that's the way to understand electron dot structures. And then there are different compounds with who are molecular in nature, basically who generally those who form single molecules. They exist, for example, chlorine, fluorine, bromine, iodine. I have given you all of those examples, including nitrogen and oxygen atoms, hydrogen gas. They're all single molecule compounds. This is not similar to ionic compounds. Ionic compounds come as crystals or a huge, for example, diamond. The entire diamond is like one molecule. They are connected across to each other in a definite format, right? So they are completely like one molecule, but here you will have single small molecules in place. And most of the covalent compounds will be water insoluble, but they'll be soluble in benzene, kerosene, or petrol, because benzene, kerosene, petrol are all what you should say non-polar, and therefore non-polar substances are soluble in non-polar substances alike. Then we are seeing covalency, covalent compounds, covalency. We have seen allotropy. In allotropy, we have seen that you have to distinguish it as crystalline and amorphous. Fullerenes, another class that we saw. We saw the formation of very large number of carbon atoms and catenation property, definition of catenation, and its reasoning is what we had seen in the slide. Then we saw hydrocarbons classification as saturated and unsaturated, majorly. And then the definitions of saturated, their examples; unsaturated, their examples with alkane, alkene, alkynes. Then we are also seen isomerism. So isomerism is where it has the same molecular formula but different structures. Please do not mix up isomerism with allotropes. I have said this again and again. Then we are also seen how to write iso, neo, sec, all of those. We have seen functional groups. What are the functional groups and how do we name them? We have seen homologous series, especially the homologous series with methane, ethene, and alkyne. All of these three put together. We have also seen how to really write answers for homologous series, their definitions as well as the examples. We are also seen the nomenclature rules, the IUPAC rules, the common names. So the ones in red in this PPT are the common names, where the ones in blue are actually your IUPAC names. So then we have seen what were the roots. So we have seen the root for all the 10 carbon atoms. We are also seeing what are ethyl, iso, neo, tert, uh, all of those prefixes. With these prefixes, you can actually understand how alkyl group gets attached. We are also seeing the rules of nomenclature. For example, we take the longest chain, and then sometimes if the longest chain is not straight, then you have to actually write through the substituent to form the longest chain. Again, here look at the red ones. The red ones are common names. The blue ones are actually IUPAC names. The red ones consider all carbons together. The blue ones do not. The blue ones actually break down the carbons to the only number of carbons in longest chain and not others. So that's one. Then you will find that IUPAC nomenclature, these are the rules. Firstly, to take the longest chain. The second one is to actually name the parent atom depending on the longest chain, and then name the substituents on it. Then we had seen di to suffix with di, tri, tetra, giving them some numbers. The final thing that we saw, that how the numbering has to be done, and writing the name in alphabetical order. While you write in alphabetical order, di, tri, tetra does not matter. Even while numbering, ethyl, methyl, propyl, dimethyl does not matter. Only matters is the root that you are using, ethyl or methyl. If there are same substituents on either sides, you will use the one that gives you least number. So you'll find that here we will write it as hexane because there are more substituents on the root and there are less substituents here. So you use the one that with more substituents. The naming functional groups is what we have seen. All with all the functional groups we have seen this. We have seen four different reactions. In combustion, we have seen two now, which is basically complete combustion and incomplete. We have seen important compounds of carbon, which is ethanol and ethanoic acid. And the last one we saw was soap and detergents, cleansing action of soap and their differences. So that's the entire chapter for you. Now a few points to note, right? Some common instructions, because this is the last session for you guys in terms of the crash course. Of course, we will be solving papers and we'll be meeting quite often going forward. But some points that I would like to mention here on this session right now is, the first one is that always yeah. So one second. Uh, yeah. Yeah. Now, let me write here. Yeah, few points. First, always check how many marks is the question for. Okay, how many marks is the question for? Now, once you know the marks, then always try and see if there are multiple parts to it. Let's say part A, part B, part C, and let's say the question is for 5 marks. Okay, then definitely one will be for 1 mark and the other two will be for two marks. It is rare that one is for 1.5 and 1.5. That is rare. It's always 1 to 2. Whenever it is a 1 mark question, you are always expected only 1 point and an example, if there is an example. If there is a 2 mark question, you are expected to write 2 to 3 points. Always write 3 points and then an example or something. Again, here also 2 to 3 points and then an example. If there is a problem to be solved, explicitly mention the formula. The formula is something that will always fetch you marks. Even if you get your answer wrong, please note that sometimes in the hurry you make calculation mistakes and all of that, you end up getting a wrong answer. Please write the formula in the answer, which is important to have. Okay, so these are the first few questions. Now second one, whenever you write an answer, it is a good idea to actually write the answer with the answer. Remember writing the answer number, whether it is answer number, answer 1, 2, 3, 12, 13, 14, whatever it is, always write it there. If you by some method you were not able to complete the answer, if you're scratching it up, either scratch completely, and if you're attempting it at the end, go there and write 11 and then attempt. I have seen people attempt half the answer here and then half the answer at the end of the paper. Not allowed. Not allowed. It is very rare that you will be getting marks in such situations. It will No marks will be given to you. You will lose marks in either of those, or you will simply end up getting marks only in one. So please do not do this mistake. If you're attempting an answer, attempt it at the same position. Once the answer is finished and you feel, or you're not getting the answer for some reason, and you feel that you really need to answer it at the back, simply scratch completely. Okay, so that's another uh, that's another reason for this. Okay, I'm not sure if this is clearly visible to you. I'm going to use a different color. Or maybe it's not visible, so I'm going to use a different color so that you can remember that, you can realize that. Okay, the next is, always try to solve questions. So there are ways that people generally solve the questions. Either they go by numbers, 1, 2, 3, as the questions are there in the paper, or they have a different method that they'll solve all physics earlier, all chemistry later, and all bio later. I propose both of them. Okay, there is no difference in either of them, right? If you feel that you can do physics, chemistry, bio separately, please do that. If you feel that helps you writing answers better and memorizing answers and giving a better performance, absolutely okay. So whether you go chronological or physics, chemistry, bio, ideally it is nice to get physics, chemistry, bio separately, because when your papers go for correction, generally they go for correction to maybe multiple people. So if there is a bifurcation for correction, generally it would be through either a physics, chemistry, bio kind of a correction. Sometimes they also go number wise. So first 5 to one teacher, next 5 to other, and then the next 5. In either ways, the getting through the number is a very easy part to do. So but getting through the physics on chemistry part is a difficult one. So I would recommend that if you're using that, go forward with it. You can write all physics earlier, all chemistry and all bio. Having said this, please don't spend time in doing this bifurcation. It's useless. There's no point of doing that. So waiting, really searching, you're not finding a physics question. Sometimes a physics question was forgotten earlier. Sometimes it so happens that you mess up the entire order. You don't know whether you have solved the entire paper or not. So it's a good idea to tick a question number once you have solved it. If you have not really solved it, put a question mark and go forward. Okay, So tick or put a question mark. Second is that do not attempt to write both the ors. No, useless. I've seen people attempting both or questions, feeling that at least in one they will get some marks. No, whatever you're most confident, just write that and move on. It's just going to consume time for you, and you will end up forming getting only the same amount of marks. So only write one answer which you feel confident. Do not attempt the second or question at all. No matter you how confident you feel that you are going to impress the teacher with that, doesn't work. Doesn't work. Okay. So these are the few points. The next few points are, what I'll recommend is that have a good handwriting. Very, very critical. Very critical. Have a good handwriting. Okay. Without a good handwriting, forget getting a centum in science. Okay. Not possible. Have a good handwriting. Have a good presentation. It's always very nice to write in paragraphs, or to write point wise. Okay, write in paragraphs or write point wise. Both of them are very, very okay. Okay. I would recommend to write either of that, whatever you're comfortable on. Most important is draw diagrams. Also, when you draw diagrams, do not sketch them like you are sketching out of your hand. Okay, like, no, don't do. This is a beaker, and with a for example, a conical flask, you simply draw like this. No, very bad. You can use this only if you are completely short of time. You feel that you don't have enough time, and the bell is going to ring. Then you can use your hand drawings. But as far as possible, use scales. Use proper geometry material to draw good diagrams. Always use both pencil and pen. Both pencil and pen. Only pencil or only pen is something that I don't recommend. Only pen also I definitely don't recommend, but only pencil also I don't recommend. Generally, you should draw the diagram with pencil. Use a dark colored pencil. Don't use light pencils. Okay, use good pencils. Use erasers very well. Do not overwrite or overdraw. Do not keep on doing this, or do not write C C C C on top of it. No, bad habits. Okay, bad habits. Do not do that. If you feel that okay, you have written something, just put a small two-line cross and write next. Just a 2 or 3 line, maximum 2 or 3 line. Do not dirty your page. Okay, do not dirty your page. Presentability is very important. Now, generally in the diagrams, label with pen and draw the diagrams with pencil. I'll tell you why. Because the pen marker will remain for a very long time, and therefore most of the marks are generally for labeling. They give it for labeling. So if your labels are good, you'll end up getting a lot of marks, even if there is a problem with your pencil where someone was not able to read it or something of that sort. Okay, so do that. The next is that when you solve mathematical questions, it is good to do step by step and box it. Okay. Once something you have written, for example, x is equal to 3. Okay, just box it. In chemistry, you can very simply put an underline. Very good habit to underline. Okay, please underline. Simply 2 lines. And underline doesn't mean that you have to take a scale and keep on underlining. No, you have written okay, ethane. You have written something like ethane. Just go and underline it softly with your own pen. Okay, own pen, or even if you want to do it with pencil, that's okay. The one last important point: always check your paper at the end of the exam. It's very, very important to check your paper. If you feel that you're done with entire subject, it's a good idea that you can just go through the paper and make sure that everything is written, everything is in place. Okay, do the checking of the paper at least 10 minutes prior. As the exam time is coming closer, do the checking of the paper at least 10 minutes prior. Now, whatever I've said, why I'm saying this so early is because in all the upcoming exams, try to use this strategy, because that will become a habit for you to attempt in the board exams. Once you use this strategy over and over again, you'll realize that at some point of time it will just come naturally to you. Okay, so that's a very important point. I'm just going to pause here for a minute or two. I if there are any questions that you have, please feel free to drop it on the chat, and I'll be happy to answer them. Yeah, so just feel free to answer, ask up any questions, and I would answer them here. So if there's anything that you feel to ask now, we are just come to the end of the today's presentation. I'll be happy to take up your queries. Good to see you all you guys. I think it's nice to really connect. Yes, if you have questions, please feel free to ask, else we'll be pausing in a few minutes. Okay, so it seems that you don't have any more questions. Then I'll wish you the best, and I will suggest that you do your uh, okay. So that's nice. Then I'll wish you all the best. Thank you so much for being here. I hope you are studying well, and if you have any questions, you can always reach out to me on WhatsApp or any other means. You can always call me. And I wish you the best. Please feel free to yeah. So study well and attempt your exams pretty well. Thank you so much. Bye, Shreyas. Thanks, guys. Kritika, Anirudh, and all the others. Thank you. Okay, so Mehul is saying, why is sodium kept immersed in kerosene oil? So Mehul, it is because sodium is very reactive. So if you keep sodium in air or with moisture, you will find that it just explosively will react to form sodium hydroxide. So therefore, it is kept immersed in kerosene oil because kerosene oil is very unreactive. Kerosene oil is flammable but not reactive. There is a difference. Flammable means if you bring fire, then it will burn. But if you just keep it, then it does not react by itself. Yeah, so that's the reason that it is under kerosene. Okay, any other questions? I'm here if there for another minute or so if you have questions. Else, thank you so much. Take care. Bye bye. Thank you, Mehul. Thanks so much, everyone.